people are coming, but no, let's start. So we are glad to have Michael McBreen now from Chinese University of Hong Kong, former at Harvard. And he will speak about symplectic duality and twisted quasimaps. Michael?
Thank you so much for having me. It's a pleasure to be virtually in Kansas. So this is all. Oops. This is all joint work with Artan Sheshmani and Shing-Tung Yao. And so let me give you sort of just the briefest of outlines. So I'll tell you what all of these objects mean as we go along. But the point of this talk is to start from a hypertoric variety, kind of holomorphic symplectic variety. And to produce two new, much larger varieties. Both sort of not of finite type. So if we call this hypertoric variety X, we're going to produce the periodization of X and the loopification of X. And use these guys to study enumerative geometry of X. And so, in some sense, the spirit of this work is basically sort of a concrete realization of the idea that Gromov-Witten theory of X or quantum cohomology of X should have something to do with the loop space of X. And so, of course, there are already many realizations of this, and this is kind of a slightly different flavor of this idea. So, okay, so let me start with some definitions. So conical symplectic resolutions. This is a family of spaces to which hypertoric varieties belong. CSR for short. So what you're given is an algebraic symplectic variety X. That's algebraic symplectic. And a C star action such that the symplectic form omega is scaled by some character of the C star. Okay. And moreover, if you consider the map from X to its affinization, meaning the spectrum of global functions on X, this guy is proper and birational. So, okay, so how should you think of this? And one more condition. Where does the word conical come in? Well, the C star action upstairs induces one downstairs, and this downstairs space is contracted to a point, so it's a cone. So you should think, in some sense, maybe you can start with this cone, this spec of OX, and X is some symplectic resolution of this conical singularity. So that the words proper and birational tell you that it's a reasonable notion of resolution. And that's what a conical symplectic resolution is. So, okay, so examples of such a thing. include, so the sort of the original example that motivated a lot of the work in this area is the Springer resolution, so the cotangent bundle of the flag variety of a reductive group. Another famous example is the Hilbert scheme of points on C2. So if you're an algebraic geometer, you know that the Hilbert scheme of points on a smooth surface is smooth. If you take C2, you get some smooth symplectic variety, and it resolves the child variety of C2, so just symmetric powers of C2.
So the downstairs space is what is a nilpotent cone in the first case and symmetric power in the second. Yeah.
Exactly.
Actually, I do not see the bottom of your. Okay, now it's better. Okay.
Okay. I think sometimes there's that little bar of commands at the bottom of Zoom that hides. Yeah, so that's right. So typically, these spaces come up in geometric representation theory, essentially because, well, for let's say two different reasons. You can quantize X. So and you'll get some non-commutative algebra.
Algebra or sheaf of algebras?
Well,
it's affine, yeah. Yeah, okay. Probably.
I mean, you can take global sections, let's say, of the sheaf quantization. Both are interesting somehow, but just for simplicity, we'll take global sections here. And in these cases that I just highlighted above, you get well-known objects of representation theory. So actually, I'm giving myself a little more space here. It's something you can't do on the blackboard. So here, U of X is just a universal enveloping algebra of X of G, sorry, at a central character. And here U of X is a Cherednik algebra. So the quantizations of these symplectic resolutions tend to be algebras of interest in representation theory. And well, you could ask, how can that be? We go back up here to our definition. This is a sort of purely geometric definition, and it seems like you could get any number of bizarre things out of it. But actually, it's very restrictive. So there's really all symplectic resolutions fall into some finite number of families. So it's a little bit like simple Lie algebras, where in the end, despite the very general definition, you can associate some finite number of families of Dynkin diagrams to them. All right. So that's one thing you can do at X. The second thing you can do is you can study the enumerative geometry of X. So I mean that in a kind of a general way. So for instance, if you take quantum cohomology, you get a commutative ring. If you take, let's say you can study the I function, you get some differential equations. And let me just say sort of vaguely, you get more representation theory this way. So it's just an example. The quantum differential equation of T star G mod B, which was studied by Braverman, Malik, and Kunkov, is the famous affine Nizhnik-Zamolodchikov equation, or connection rather. So these days, people have started to understand that there's some relation between these two, let's say, aspects of X. It's quantization and its enumerative geometry. So, so let's say that the sort of the vague question, which I'll make more precise in a second, is relate quantization of X to something like maps from P1 into X. And we'll find that actually this is not quite right. We should relate the maps from P1 into a different symplectic resolution, X shriek. Well, okay, so we'll get back to that. But this is somehow, this is where we're going.
Why they should be related at all?
Well, no, that's not at all. You know, at first sight, that's not at all obvious. Once I like get around to explaining X shriek, it will be a little just mildly more clear, but I'll get to it. Okay, but first I need to say a little more about quantizations, just to sort of set the scene. So back to quantizations. So how do quantizations work? So you pick, so quantizing X in more detail. So you pick eta, a degree 2 cohomology class. You sort of think of as arising from a symplectic form. And this is going to specify a deformation of the structure sheaf of X into some non-commutative guy, and consequently taking global sections, you get this non-commutative algebra.
This non-commutative guy, does it live over formal series or what?
So, right. At first it lives over formal series, but because of this C star action, that contracts the affinization to a point, you can consider the subalgebra of guys that are sort of C star finite. So you have C star act on the deformation parameter on the Planck constant. And you consider, you know, basically the polynomial subalgebra. So this is an algebra over polynomials in the Planck constant, and then you can set the Planck constant to 1 and just get an algebra. So this is over C. Or if you prefer, over C polynomials in each bar. So this is one feature of symplectic resolutions. They have sort of global quantizations, not just asymptotic. Okay. So as I said, one example of UX is the universal enveloping algebra, and in general, this quantization shares many features with the universal enveloping algebra of G, the central character. So in particular, we can define a notion of, it's called category O for this guy, certain category of modules. So given a torus acting on X, this is a Hamiltonian torus. Hamiltonian in the sense that it preserves the symplectic form. It's generated by Hamiltonian transformations. And a co-character of A we have a category we have given a Hamiltonian torus acting on X and a co-character of this torus, we can define some subcategory of modules over the quantization, which we call category O by analogy with the sort of category O of Bernstein, Gelfand, and Gelfand, which is basically modules equipped with a compatible A action and weights under this action, which are bounded by our co-character. So if you've ever seen the picture of, let's say, representations of SL2, where you have, a raising operator E, a lowering operator F, and then a diagonal matrix H, Cartan matrix, and you use the Cartan matrix to diagonalize your representation, and E and F to go between eigenspaces. Well, this is a great way to say representations of SL2, but this method generalizes basically to category is in some sense the largest category to which this method can usefully be generalized in a certain sense. In particular, it's engineered so that objects in category O have the highest weight. So you can sort of reconstruct them from their highest weight spaces.
And how this highest weight is interpreted in terms of the sigma or whatever?
So let me, yeah, I can say that below. So I actually sort of started explaining this when I was cut off. So given some object L, so I'm down here, given some object L in category O, we can take its support. That's a general thing you can do with it. Appropriate representation of the quantization. So you get some Lagrangian inside X.
No, but in general, you do not have Lagrangian, you have just coisotropic.
Right. So the feature of category O that you get these, yes, that you get Lagrangians. Thank you. Essentially, and it'll be clear why in a second. So in fact, this Lagrangian for category O is going to be contained inside the attracting locus of sigma. So this is the all points X inside X such that sigma Z of X goes to the fixed locus as Z goes to 0. Okay. So if I draw a picture here, if this is X and these points are the fixed points, then to each fixed point I have some attracting cell for the action of this co-character. The attracting cell is going to be Lagrangian because the co-character is because the action of A is Hamiltonian. This is Lagrangian. And the support of any module in category O is going to be contained in the union of these Lagrangians.
So basically, if you fix sigma, you have kind of a complex Lagrangian skeleton, which is singular. It's smooth. It depends on how XA. Yeah.
So for a symplectic resolution, it will almost always be singular. If you, at least for the sort of in the setup that I'm considering, basically, if we go back to the definitions here, if you assume the action of this C star action, the existence of this C star action that contracts the spectrum to a point, then you get sort of a singular skeleton. If you drop the condition of the C star action, then these symplectic resolutions typically admit deformations, which are smooth and affine. And in these deformations, the skeleton you get is just a disjoint union of smooth Lagrangians. And so you can think of, going back down to our picture here, you can think of X as being sort of a degeneration of some smooth affine guy, X prime, where these Lagrangians are all kind of minding their own business separately. And in the limit, they start to interact. You get some big singular Lagrangian.
So which one? Okay. So both X and X prime are smooth. Yeah.
Yeah, that's right.
Okay. Which one should I think of as a conormal to something? You have this example G mod B. So
right.
Are they conormal to some orbits or what?
So for X equals T star G mod B, this attracting locus is, you're exactly right. So these are basically the conormals to Schubert stratification. So you think of, C star acting on G mod B by some co-character of G. The fixed point locus you can identify with the Weil group, and then the attracting cells of these various fixed points are Schubert strata, or Schubert cells, and their conormals are exactly the Lagrangians that I'm describing up here. On the other hand, X check, this is going to be basically a regular conjugacy class of G. So regular conjugacy class. So it's some smooth affine guy. And if you take the attracting cells and in X check, you're getting basically the sort of sub variety of the conjugacy class that lies in a given sort of nilpotent orbit, nilpotent subalgebra. So anyways, you get some smooth Lagrangians. Okay, so, all right, so category O is some category of modules over the quantization, and you can sort of think of it as modules that are supported on this attracting locus, which depends on a choice of co-character.
So this is exactly true for T star G mod B when you use this Williamson-Bernstein localization theory. You have modules of the universal enveloping algebra with a trivial central character, and these are characteristic varieties of of the corresponding D module. Yeah.
Exactly. Exactly. So yeah, so in some sense, the point of symplectic resolutions is sort of to extend this theory that was developed by Beilinson and Bernstein and Kashiwara, Belinsky, and many other people to sort of to algebras that are not necessarily semi-simple Lie algebras. So, for instance, the Cherednik algebra, or to various other sort of non-Lie algebras that arise in physics, for instance. All right, so this is all I want to say about quantization for now. So now I have to introduce this actor X shriek. What is X shriek? I told you that eventually we're going to relate quantization of X to enumerative geometry of X shriek. So, right? So really, I want to discuss the symplectic duality. We say X and X shriek, so two conical symplectic resolution, are symplectically dual if we have the following picture. Oops. So we have our torus A, which acts on X. We have another torus, A shriek, which acts on X shriek. We have the degree 2 the homology torus of X and the degree 2 homology torus of X shriek. And we have an identification of the sort of Hamiltonian tori and the homology tori of these two guys. So that's part one. And given a choice of quantization parameter, which
does it have integer?
Yeah. Here I'll pick an integer one. This is somehow just for convenience's sake. It's not that you can modify this for other values. But this particular integer lattice is equal to by this identification is equal to sorry, did I do something funny here? Yes, I did. I didn't mean to write h lower 2 here. I meant to write h upper 2. So this guy is equal to just the lattice of co-characters of A shriek. Likewise, given.
So the notation is what? Can you just write it down?
Yeah. So let's say. Well, let me put it this way. So given eta in here, and given sigma.
So it's integer Lie algebra of the torus.
Yeah, but I'll rephrase it so I don't have to write it that way. It will be better. So given a choice of eta and sigma, a quantization parameter and a co-character, we get by this identification we get a co-character of the dual torus, the the Schrichtors, and we get a quantization parameter for a Schricht, and we require that category O of X for these parameters eta and sigma is causal dual to category O of X Schricht with parameters minus sigma minus eta. Okay, so we not quite that.
Not okay. What does it mean that it's causal dual, the level of categories? And even when you explain it, it's sort of a very strange definition. It's like for people here doing mirror symmetry, as if you define the mirror dual as such for which the Fukaya category is equivalent to dB Koch.
Right.
How to check it? But what is causal dual first? Yeah.
Yeah. So causal duality is right. It's somewhat annoying to define, but essentially the idea is so the sort of the basic example that you should keep in mind for causal duality is, suppose you're interested in studying modules over the symmetric algebra of some vector space.
No, this I understand. If you have algebra, then you take just causal dual. But as for the category, I don't know. What do you mean?
Right. Well, so basically, it means that both of these categories have graded lifts, meaning that you can assign some weights to the objects in the category. So, all right. So essentially, you can look. Let's focus on the left-hand side. So on category of O of X, you can look for certain special, given a simple object, you can look for certain special projective resolutions of this object, which are linear in the sense that the weight of the ith term is equal to I.
Okay. And you take endomorphisms of that and take probably the dual, causal dual or something like that, yeah?
Well, essentially, in some sense, the point is that this you can make this sort of such called linear projective resolutions into another abelian category, whose simple objects are going to be basically
projective for the other one.
Yeah, that's right. So just like a single projective object in a single place, that's a projective resolution of itself. But that's going to be a simple of this new category, whereas the projectives of this new category are sort of going to correspond to simple objects of the old category. So you have it's basically a sort of a duality that exchanges simples and projectives.
Yeah, but in terms of geometry, since your objects have support, how can I can I, looking at the support, distinguish which are simples?
So that's typically no. It's so even with something like just characteristic variety of a D module, right? It can be difficult from the support to tell whether something is simple or not.
Okay, I should really take indeed the perverse extension from something sitting on the Schubert cell. Yeah, okay.
Yeah. So
oh, yes.
So you mentioned homological mirror symmetry. So yeah, this is sometimes called three-dimensional mirror symmetry, sort of by contrast with 2D mirror symmetry, which is the famous mirror symmetry, because it arises in a kind of a similar way physically as 2D mirror symmetry, but when you're considering a sigma model for a three-dimensional domain, 3 real dimensions. But that being said, the sort of, for 2D mirror symmetry, you can say, well, 2 varieties are mirror dual if they're SYZ mirrors. You know, if they have dual Lagrangian torus vibrations, you dualize you find some Fourier-Mukai kernel on this dual vibrations, and this produces an equivalence of categories. Fine. I mean, this somehow doesn't always work out exactly as planned, but it's a good sort of way to think about it. So in the case of symplectic duality, this funny definition that I gave is really what came first. This is due to Braden, Proudfoot, Licata, and Webster. And basically what they noticed is that for a certain class of, first of all, that this definition is satisfied when X is T star G mod B, and X shriek is the Langland's dual resolution, where then this is a theorem of Billinson, Ginsburg, and Zergel. And so that was a famous theorem from that has been known for a while. But they noticed that the same setup also applies to some other conical symplectic resolutions, including the hypertoric varieties that I'm going to talk about today. So this is sort of an extension of the results of BGS, Billinson, Ginsburg, and Zergel, to more general conical symplectic resolutions. And again, it was first sort of noticed and proven kind of as I stated here, as an algebraic relationship between 2 quantizations. And so now the geometry of this relationship is a little better understood, but it's still it's a bit involved in the sense that the construction of X shriek from X is rather complicated, very sort of indirect. It involves, you know, convolution algebras and cohomology. So it's much less intuitive than dualizing a Lagrangian fibration. So it's very difficult to just point at, you know, some piece of X and say, like, where does it go in X shriek? So somehow maybe this is one has to start with this algebraic definition and hope that one can understand something about it. Sorry, is there any more questions before I continue?
No questions, so then go ahead. Yeah.
All right. So okay. So let me now I asked a sort of vague question earlier. Let me refine it a little bit. So it will still be rather vague. So now let Z of X be some generating function from enumerative geometry. So without telling you exactly which yet, I'll just give the sort of general form. You try to do some sum over curved classes of some virtual count of maps from G1 into X, such that the degree of this map is equal to the given curve class. And you record this degree with some formal variable, Z. And so the question is, can you describe Zx in terms of X shriek, and eventually in terms of the quantization of X shriek? And so this kind of question has been sort of approached in various ways in many works now. So there's work, I think in progress of Aganagic and Akunkov, which basically relates quantum cohomology of X and X shriek. there's some work with some physicists, Bullimore, Dumafte, Hilburn, mathematician, and Gayotto. There's a paper of myself, Kamnitzer, and Proudfoot. There's some recent work of Smirnov and Zhu. So, okay, so all of these papers sort of take a slightly different definition of this question, or sometimes a rather different definition, and produce like a meaningful answer. So this is somehow this is a general frame for producing a lot of interesting conjectures. Okay, so I'm going to describe sort of yet another version of this question and yet another answer, which is a rather different flavor from the ones I mentioned here.
But when you say in terms of X-Shrik, what kind of data, kind of people, I mean, these people, what kind of result? Z of X is what?
So for Aganagic and Akunkov, in some sense, let's say, so here Z of X will mean a different thing for each paper, but for Aganagic and Akunkov, the result is something like Z of X depends on some Kähler variables and some equivariant parameters. And essentially they say that, well, in their setting, they're considering, you know, the K-theoretic I function of X, that it's sort of equal to the one for X-Shrik once you exchange these parameters. Whereas just
easy to compute. I mean, for mirror symmetry, of course, the whole starting point was to compute something difficult in terms of something easy, like Gromov-Witten in terms of periods. Which one of these is easier?
Good question. So a priori, neither is easier. It's really a completely symmetric statement. But that being said, in any given case, it could be that you know more about one than the other. Because let's say that these can have, let's say the quantum differential equations can be different ranks. So it could be that the rank on the dual side is equal to 1, let's say, whereas the rank on the original side was high. But maybe, I think for Aganagic and Akunkov, so they use the sort of interplay between X and X-Shrik to actually compute the monodromy of the quantum differential equation on X. So they, I mean, it looks like magic. It basically is magic, but they sort of, by hopping back and forth between X and X-Shrik, they manage to tell you something extremely non-trivial about X, namely the monodromy of the QDE. So I mean, I don't have time to sort of go into how they do it, but that's, I'd say that's a strong evidence in favor of this approach. And then just to cite something which is a little closer to what I'm going to do today. So in this paper of myself, Kamnitzer and Proudfoot, so again, we take a sort of a slightly different but related, let's call this one AO, this one is KMP, generating function. And we show that this is, let me actually just write Z of X. This is equal to something like the character of a module in category O of X-Shrik. So essentially, yeah, it's telling you that something, it's basically a sort of specialized version of an I function of X can be recovered as a character in the sense of, just like the characters appear in the Val character formula, of some module in the category O of the dual guy. And in this example, I would say that arguably the right-hand side is much easier to compute than the left-hand side. so. Not only easier to compute, but just easier to prove things about. So this is what I'm going to talk about today in my few remaining minutes is sort of analogous to the second relationship. Okay, so now I have to hurry up a little bit. I've maybe lingered a little too long. Quantizations. So, okay, I have to tell you what a hypertoric variety is. These are also called toric hyperkahler varieties. I think there's some controversy in the field over what the correct name should be, and you know, I don't want to make any enemies, so I just say both. But so basically, they're hyperkahler analogues of toric varieties. The way you get them is by taking a torus called G, acting on the cotangent bundle of a vector space. You pick some character of this torus, sufficiently generic, which you use to linearize this action. And then you take the GIT, well, you take the GIT quotient of a zero value of the moment map for this action. So you get a symplectic variety, which actually is a conical symplectic resolution. So yeah, so these are sort of algebraic symplectic versions of toric varieties. They're not toric, but they share many sort of many analogies with toric varieties. So they have sort of a combinatorial flavor. You can think of them as geometrizing matroids, if you're a combinatorialist. And as a special case of this construction, given any graph gamma, you get a hypertoric variety x sub gamma, which is just equal to the cotangent bundle of c to the number of edges of gamma, reduced by c star to the number of vertices. And this space encodes a bunch of features of the graph. So for instance, if I take this little graph, I get x equal to the Crepin resolution of C2 mod Z3. And if I take this graph, I get the cotangent bundle of P2. And so, yeah, so to any graph, you get a hypertoric variety. So these are sort of if you're studying symplectic resolutions, hypertoric varieties are a good place to start because, well, they're a very big family, but they can be studied sort of combinatorially, much like toric varieties. So in particular, we know a lot about category O. So this has been studied by, in some sense, before these particular definitions were fixed by Mousson and Vanderberg. And then once they were fixed by Braden, Licata, Proudfoot, and Webster, it sort of defined the appropriate context for this in general. And so simple objects of category O, in this graphical case that I just mentioned, these are in general, they're in bijection with fixed points. In this graphical case, these are the same thing as spanning trees. Okay, so just to give you a sort of indication of the sort of combinatorial flavor. So, all right. So we want to sort of we want to answer the question which I posed earlier, namely get the relation between Zx and X shriek for hypertoric varieties. And I'll focus on the graphical case, which is actually nothing special about the graphical case. It's just easier to describe. So for that, we need to introduce non-finitary hypertorics. And we'll warm up with graphs. So before I tell you what a non-finitary hypertoric variety is, I'll give you some non-finitary graphs. So here's a graph gamma. I'm going to produce two new graphs. One of them I'll call periodization of gamma, and the other I'll call the loopification of gamma. So the periodization is given by taking gamma and then subdividing it into many segments. In fact, I subdivide each original segment into z many segments. So you get sort of a non-finitary graph. Okay? And so this is in this case, you just get a sort of infinite chain. On the other hand, the loopification is obtained by taking, again, our graph gamma. And then you start multiplying the edges. So rather than subdividing them, you add more edges in parallel. So again, you do the z many times. So these procedures are kind of dual to each other, adding edges in sequence or in parallel. But in both cases, you get a graph which is no longer of finite type. So now we can sort of repeat the same thing, but for hypertoric varieties. So we start with our hypertoric X, and we produce two new hypertorics, which are going to be not finite type varieties anymore. So the periodization of X and the loopification of X. And so if X, let's say, were the cotangent bundle of P1, then the periodization of X would look like an infinite chain of P1s. Sitting inside a symplectic surface. Okay. On the other hand, the loopification of X would look like the cotangent bundle of P infinity. So this guy here is sort of analogous to the universal cover of the loop space of X, whereas this guy is sort of the periodic version of X. And the definitions of these two spaces are actually not, they're fairly straightforward. So they're very big spaces, but they're not very complicated in some sense.
Are they kind of inductive limits or something like that?
That's right.
Yeah, okay.
Yeah.
So first you take finitely many segments or finitely many edges, and then you kind of increase, something like that.
Exactly. Exactly. But the point is that these are these new guys, despite being, you know, rather infinite dimensional or infinite type, you can treat them more or less the same way you did your original hypertoric variety. So these are both, in some slightly generous sense, hypertoric. In particular, we can consider category O of this loopification. So we have a torus acting on the loopification, which is given by the original torus. Let me put it this way. We had an original torus T acting on X, which I think I called it A originally. Torus A. And we have a slightly bigger torus A cross C star, which acts on the loop space, where this is basically loop rotation. And so you can consider co-characters for this bigger torus. So let sigma plus be a co-character with a positive component in the rotation part. And sigma minus be a co-character with a negative loop rotation term. And so the attracting locus for sigma plus is, again, analogous to holomorphic loops in X. And the attracting component, attracting locus for sigma minus is like anti-holomorphic loops.
Anti-holomorphic or sort of loops in the negative power. Because
yeah, maybe
you have to, then probably you will intersect like people do in.
Yeah. Yes, if you prefer. Yeah, let me just call it anti-holomorphic, but yes, it's maybe not a.
No, it's misleading.
so I take your point. It's really this anti-holomorphic is only sort of accurate on the unit circle somehow.
Yeah.
But yes, so really what I mean is inverse power series in Z inverse instead of Z. Just since I'm sort of already a little over time.
No, it's okay. I mean, you can go over time. It's not a problem.
Okay, so then maybe let me just say, I can even rewrite this a little better. So something like spectrum of CZ into X, and spectrum of and really, so in fact, maybe it's better to say that it's analogous to just polynomials in Z and in Z inverse. So that's sort of a feature of these spaces. They're more like polynomial loops than like power series. Okay, and as you're pointing out, people like to intersect these guys, and we like to do that too. So you can basically, so you have an action of integer homology on the loop space, which if you think of this is a universal cover of a loop space, that shouldn't surprise you. This is the fundamental group of space of free loops. And so given some class beta here, we can consider the attracting set intersected with the beta translate of the repelling set. And this, again, this is analogous to maps from P1 into X of class beta. So we find that there's some potential relationship between category O for these two different parameters, and yeah, maps from P1 into X. So, okay, so now I can finally state the first theorem. So this is, again, this is this paper tracked with Artan, Sheshmani, and Shing-Tung. So first off, so simples in category O of this loop space are indexed by, so a point in the fixed locus of X and a curve class in XZ. And so the theorem is that the X group of a pair of simples 0, L0P, so 0 is the curve class, P is the fixed point. And L beta P, so here this guy is in category O eta sigma plus, and this one is in category O eta sigma minus, so sort of in the holomorphic holomorphic and anti-holomorphic category O's, although notation is it's been questioned. Anyway, so that this X group is equal to the cohomology, some moduli space of twisted quasimaps of class beta.
What means twisted?
So, right, usually a quasimap on P1 into a GIT quotient would be a choice of some bundles on P1, and then some sections of those bundles satisfying some stability condition. So,
but these categories, I mean, they are thought to be much worse because your spaces. So I'm a bit confused. Your space, your X is taken in the category O for what? For which?
Right. Good point. So I've picked objects in two different categories, and I'm taking X between them. But you can consider X inside a slightly larger category that includes both sigma plus and sigma minus, basically.
Yeah, I understand that it's precise quantization of this intersection of two Lagrangian skeleta. Yeah. Okay. So there should be some bigger category in which you can intersect. Yeah.
Yeah. So the twisted here, it's really, I mean, it goes back to, I think, he's probably, I don't know that he's the first person to have studied this, but Diaconescu had this work on yeah, basically on sort of twisted quasi-maps into the Hilbert scheme of points on C2. And that was extended by Bumsik Kim to sort of twisted quasi-maps into more general symplectic, Nakajima quiver varieties, for instance, which are a class of symplectic resolutions. So basically the idea is you take the sort of usual definition of quasi-maps and you twist some of the bundles on P1 by some, let's say by the canonical bundle of P1. So you, what can I say? Instead of the usual situation, maybe you have P1 and you have some bundles, U1 and U2, and some maps between them. In this twisted situation is just more like X goes to U2 tensor KP1, but Y goes from E2 to E1.
I think he called them ADHM pairs or something like that.
That's right. So yeah, that's right. Thank you. So I'd sort of forgotten the name, but when you're considering the Hilbert scheme of points on C2, or more generally the moduli of frame sheaves on C2, which is the ADHM space, then these are called ADHM pairs. And more generally, you just call them twisted quasi-maps. Okay, so we have, so that's our first theorem. In some sense, it's halfway between a definition and a theorem, as in the proof is very simple once you set everything up. But what it tells you is that the sort of loop space that we've constructed is a useful way to look at the enumerative geometry of X, sort of twisted enumerative geometry. But now getting back to the question I set out originally, and sort of finish with that. I'm now quite a bit over time. So suppose X and X shriek are symplectically dual hypertorics. Then, so number one, if you think of the loop space of X as a sort of infinite dimensional symplectic resolution, you can ask what its symplectic dual is. And you find that it's the periodization of the dual of X. Okay, so these two sort of constructions, loopifying and periodizing, are dual to each other. And so applying symplectic duality, really meaning, in this case, causal duality, to this X group, we find that, so the generating function Zx for Betti numbers of this twisted quasimaps is equal to a character of a certain module over the periodization, the quantized periodized space, called a tilting module. Okay, so this may not be super familiar if you're, I mean, they come up a lot in representation theory. So, you know, simple objects, projective objects, injective objects play a big role in dealing categories, and tilting objects are sort of yet another class that you should think of as a little bit like simples or projectives, but that they sort of, yeah, they come up a lot.
Yeah, but this, when you write this kind of, let me call it universal enveloping algebra for Px dual, I mean, even without P, it's big enough as a vector space, it's infinite. Is it some kind of like universal enveloping algebra of loop algebra? What size of this?
Right. So the statement I made here is a little bit of a, it's a little bit of a cartoon. So in fact, we do not literally take this. In principle, you could try and write down this UPX and get something which is, let me put it this way. PX is finite dimensional, but not of finite type. So it's an infinite, you know, union of finite type, finite dimensional varieties of the same dimension. And so in principle, you could try and describe its quantization in terms of some, let's say, finite data. But really what we do is we approximate this periodization by some sort of truncated spaces. Like you were saying, you know, you consider a sort of inductive limit as the number of edges of your graph increases. And we use this to basically define its category O as a sort of limit of the category O's of these truncations. And so in the end, this tilting module is described in terms of some limiting object of a series of increasingly large category O's of these truncated spaces. So we don't directly work with, you know, the quantization of this infinite type variety. So this is a little bit of a cartoon, but I think it's maybe the easiest way to sort of understand what's going on. So yeah, that is a sort of yet another version of the question and answer that I originally posed. So this is some relationship again between the enumerative geometry of
character of UPX dual. You just erased on the right hand side. Yeah, okay, great.
Yeah, that's right. Yeah, so yeah, and that's let me stop here just because I think I'm 15 minutes over time. So sorry about that.
No, that's okay. Very interesting. Thank you very much. Questions? So you can just unmute yourself and ask Michael a question. So.
All right, let me turn my camera on.
Yeah, actually, I have sort of a question because I just kind of opened your paper on the first page or something like that. And I saw the words Donaldson Thomas invariants, which somehow
Oh yeah.
I know something about. So in what sense I should think of, I don't know, probably the left-hand side as something related to Donaldson Thomas theory?
Yeah, so I'd say the link is, it's more by analogy than it is literal. So if you look at, so yeah, let's go back to the Hilbert scheme of points. So if you're considering quasimaps to full band of C2, well, that looks like some map from P1 to Hilbert C2. And we can draw the graph of this map. And then you can sort of, from this guy, you can produce a map, sort of a multi-map from P1 into C2, right? Just go to n branches. And so in some precise way, these quasi-maps are sort of equivalent to sheaves on C3 or on C2 cross P1. You know, sheaves with one-dimensional support.
Yeah, I understand, but it's rather a question, okay, whether I should think about these maps in terms of Gromov-Witten theory, which certainly doesn't look as Gromov-Witten. Okay, and now you explain. So it's rather Donaldson Thomas, so you consider something supported on the image. Yeah, and this is why you do not change the complex structure on your X. Yeah, because in Gromov-Witten you should take the compatible almost complex structure, which does not have to coincide with the original one. And for you, it's really kind of holomorphic maps from P1 to X with its initial complex structure. Okay.
Yeah, I think that's right. But and maybe something else I should say is that you know, in principle, you have some obstruction theory, you know, some formation obstruction theory for quasi-maps into X, which is in the usual setting, usual quasi-maps, it's really closer, let's say, to Gromov-Witten theory than it is to Donaldson-Thomas theory. So it's sort of, but in the twisted case, so when these maps are twisted, it says virtual dimension 0. And so you can check that, in fact, sort of, if you were to write down the sort of the virtual degree, you would find that it's basically equal to the Euler characteristic of the moduli space up to a sign.
Mm-hmm. Yeah, it's very, very interesting because
so in our paper we studied.
Sorry. Yeah. Oh, go ahead.
Well, it's just to explain why we were counting, you know, in our theorem, we counted Betty numbers of the moduli space. So, I mean, originally we were sort of interested maybe in these twisted quasimaps, and hence in the Euler characteristic of the moduli space. And then, well, you look at it, you see that actually you can do one better. You can not only compute the Euler characteristics, you can compute the Betty numbers via this duality.
Mm-hmm.
So, but you know, if, from the perspective of Gromov-Witten theory, it would be rather strange to be counting the Betty numbers of your space of curves. So that's the sense in which it's kind of like Donaldson-Thomas theory.
Mm-hmm. Thank you. More questions? Okay, it looks like people are silent, so there are no... Okay. Zhongzhu?
Yes, I got in late. I was at Jordan Williamson's talk. So you at the one point later you mentioned about the C-star action on the loop. Mm-hmm. So it's just the C-star. Can you how is the C-star acting on the loop space?
Well, so I mean, really the space L of X is like a loop space, but so let me just explain how C-star would normally act on a loop space. That will tell you kind of how it acts here. Oops. So, okay, supposing I have a space X, so the loop space is maps from C-star into X.
Okay.
And then you can precompose a map.
Precompose with the multiplication by C-star.
Yeah, with rotation of full.
Yeah.
Okay, Zhongzhu, are you happy with the answer?
Oh, yes. But what happens if I, instead of, let me see, I guess I can do the algebraic action. What happens if I take a finite group inside of C-star action and take a look at the fixed points on the loop space, but a finite group?
Yeah, that's a great
the
question.
cyclic group, for example.
So, right, if you take fixed points under the full C-star action, you're just getting sort of constant loops, right? So loops that you know, map the entire C-star to a single point.
Mm-hmm.
Now,
if I look at some equivalent under this finite group, homology, does that give something
interesting?
Mm-hmm.
Some orbifold version of your loop space or something.
Yes.
Something like that.
Actually,
yeah.
just in Jordan Williamson's talk, he was talking about this.
You just apply, okay. You
and
apply the knowledge from one to
what he did was he was working in the positive characteristic P case, and the cyclic group is order P element acting, and that gives the Frobenius twist in the geometric on the loop space.
Yes, that's right. And so they apply this to something like the affine flag variety, if I remember correctly. Or the
that's right, because the affine that's coming from the loop.
Yeah, so I mean, they're not totally unrelated. So for instance, you know, I know that Jordy Williamson also likes to study tilting modules, but the setting is not quite
they were using this one and gave a very quite different way of proving the character formula, which used for the tilting modules in positive characteristic.
Right. So you know, I would certainly not claim that what we're doing here is some alternative approach to what Jordy's doing. So they're somehow like the words are the same, but I'd say the content is quite different. So we certainly don't have any. This is not.
Well, if you can connect your finite subdivision to taking some action of some cyclic subgroup, I don't know.
Yeah, this should be corresponding to quantum group at the roots of units. So if you take a cyclic group, and still over complex numbers is what you are working on.
Yeah, you know, I'm sure you're right. I've never really thought about this carefully. I know that. So one thing I have thought about in this context is if you take a hypertoric variety and you take its quantum differential equation, so sorry, maybe this probably doesn't answer your question, but I'll say it anyway. So you take the K-theoretic QDE. So this is it's no longer a differential equation; it's a difference equation with a step. And the step is again, it's a little different from what you're proposing. Instead of taking, let's say, Z mod n inside C star Q, so you consider, well, it's maybe not that different. So you consider the K-theory of a point, which is just a ring in Q and Q inverse. And you specialize Q equal to
the nth roots of units, to pi over n. Yeah.
Right. And so then you consider the K-theoretic quantum differential equation, or quantum difference equation for X with step Q. Okay, and so this is a very weird object because you're considering a difference equation with that folds back in on itself. It's a difference equation that takes you around in a circle, and so you sort of don't expect it to have any solutions, but in fact it's a thing you can sort of study, and it has various interesting features. I've never really found anything I've never found out exactly how to connect it to more classical objects, but if you're interested in that kind of stuff, I'd be interested in talking about it.
Yeah, because you have this category O and you have this tilting modules, and definitely that with this finite cyclic group action will definitely, I mean, I'm sure that will on the category level. I don't know on the geometry side giving anything similar to quantum group at the roots of units.
No, it's a different story. I remember we wrote some paper with Vadik Vologodsky long ago about this Q difference equations when absolute value of Q equal to 1. It's not necessarily roots of unity, but just equal to 1. So the orbits, exactly as Michael wrote, just circles for the action of Q. And I forgot, we had some geometric, it's something like quantum torus, something like that, similar to this, but there was a pure algebra geometric answer for the category, which I forgot, but it's in the archive. It's maybe, I don't remember, almost probably 20 years old. Yeah, people consider this, and you can take next step, probably take elliptic version, yeah, instead of the theory. And so then it will be even more fun.
This is a paper with who? Sorry, with
Vologodsky. Yeah, but there were. It's not the only paper which was devoted. We were not interested exactly in Q difference equations. we were interested, I was interested in the generations of complex structures, and it's sort of a part of the story. But anyway, now I remember very little from that paper, but I mean, if you're interested. But for Q difference, yeah, it's fun, yeah. Okay, more questions? Okay, if not, let's thank Michael, who gave a talk on the very difficult constraints like quarantine and early morning in Hong Kong. So really heroic.
Quite early.
Yeah, very early. Okay, thank you very much. And may I ask you to email me your notes, so we will post them together with the video of your talk.